I hope everyone's having a real good morning. I'm Mr. H. Thank you for joining me. I have this book over here and I'll be providing the credit for that in this video, the information for this video. In the chapter on inverse trigonometric identities functions, there's a specific set of 5 questions where you have to verify these identities. As you see over here, we'll be looking at 5 questions from easy to the hardest. Book does not provide answers to these because these are verification questions. So allow this video to be a learning experience where I'll be presenting those 5 identities and I'll show you how is a good way to verify these statements. We're starting here with this arc sine or inverse sine minus x is equal to minus inverse sine x. Remember, we're going from easy up to hard. 5 questions. When you're looking at this, look at each of these separately as independent equations. And this is how I would verify. I would make this y is equal to arc sine minus x. Remember, I'm showing you one way of doing it. I would make this in another one right here because these are all functions. Y here is equal to minus arc sine x. When you look at these individually, you have to solve them individually. You'll take the sine arc sine on the other side. You'll have a sine y is equal to a minus x. You can solve for the x. X is equal to minus sine y. So that right there is a statement coming out from that part. When you look over here, you look at it as this. Y is equal to minus 1 times arc sine of x. Take the inverse sign on the other side. You're looking at a sine of y is equal to minus x. Take the minus on the other side. X is equal to minus sine of y. And you verified it. The procedure is complete because you're ending up with equal statements over here. This is equal to that simply because x is equal to minus sine y, x is equal to minus sine y, and the verification is complete for this particular question. Now this right here is the next easy one, but after this the next 3 are interesting, challenging and interesting. These 2 identities, the one before and this one, show that the inverse sine and the inverse tangent are odd functions as well. You have the definition here of an odd function. F of minus x is equal to minus f of x, just like previously shown for the inverse sine. Here again, split everything into individual functions. Y is equal to arc tan of minus x. Take the inverse tangent on the other side. You'll have a tan of y is equal to minus x, and then x is equal to minus tan of y. So this right here is done. X is equal to minus tan y. Again here, look at everything as if it's this. I'm going to separate it out. I'm looking here at an arc tan of an x, and then I've put a minus 1 here in terms of that. I'll take the inverse tan on the other side. I'll have a tan of y is now equal to minus x. Now take the minus on the other side. X is equal to minus tan of y, and there it is. Both of these are good. They look identical, therefore the verification of this identity has been completed. The next 3 questions we look at, the identities will be much more rewarding than the ones we've seen right now. Alright, let's look at this one. Arc cosine or inverse cosine of minus x is equal to pi minus inverse cosine of x. How do we verify this? We can verify it again by setting 2 separate equations. We have y is equal to inverse cosine of minus x. Let's just solve this out. Take the inverse cosine on the other side. You're looking at a cosine of y is equal to minus x. Remember, when you take an inverse on the other side, it becomes a regular function. Inverse cosine becomes a regular cosine. X here is equal to minus cosine of y, and that's what we should get right over here when we do this. Here we're looking at y is equal to pi minus arc cosine x. What we can do over here, the pi coming on the other side, y minus pi, you'll see this y minus pi is equal to minus arc cosine x. Now take this minus on the other side, so you just have an inverse cosine or an arc cosine, and flip these around because the minus will impact them. You'll have pi minus y. Now take the inverse cosine on the other side and you're looking at cosine of pi minus y. And you can use a difference formula for cosine over here. You know you're looking at cosine x minus y, something like that, but you'll have a cosine pi, cosine y plus sine pi, sine y is equal to x. You know pi in terms of sine is a 0, all of the zeros out. Cosine pi is a minus 1, so you have a minus cosine y. That minus 1 attaches with this, you get a minus cosine y is equal to x. So you have this and you have this and they look identical, so the verification procedure is complete. So you can see this was slightly more challenging. The next 2 we look at will be just a bit more challenging than this one over here. What about this one? We have to verify this inverse trigonometric identity. Inverse sine x plus inverse cosine x is equal to pi over 2. A good way of doing this is first you have to rewrite everything before you start separating everything out. Take this on the other side. You're looking at a pi over 2 minus inverse cosine of x. Now individually separate these into their separate functions. Here you'll have a y is equal to arc sine x, and you know here x is equal to just sine y. And this part right here is done. We need to somehow demonstrate this is equal to that, and we will. You know here y is equal to pi over 2 minus arc cosine x. Take this pi over 2 on the other side. You're looking at y minus pi over 2 is equal to minus inverse cosine x. Take this minus on the other side and shift the signs around. You have an arc cosine x is equal to now a pi over 2 minus y. When you take the inverse cosine on the other side, you look at the cosine applying over here, you'll have a pi over 2 minus y. You see how now you have a difference formula coming into play. We can finish it right over here. When I open this up, I'm looking at a cosine x minus y. I'll have here a cosine pi over 2 cosine y plus sine pi over 2 and sine y. You know cosine of a 90 is always a 0. All of the zeros out, but sine of 90 is a 1, and you're retained here with just a sine y. So you end up seeing that x is equal to sine y, which is indeed what you wanted. This right here very well mirrors this right here, so the verification is complete. This entire identity is true. This was equal to that, and you see in the procedure. We have one more, and that'll be the most challenging here for this video. Our last question is this. Remember, this video over here is an excellent fundamental exercise for calculus, but it's primarily pre-calculus topic. In this video, we're just doing verification of inverse trigonometric identities, but in this particular question, our statement is this: arc sine x is equal to arc tan inverse tan x divided by root 1 minus x squared. How do we go about doing this? The best thing I'm recommending you is separate this out. You have y is equal to arc sine x and work only over here. X here is equal to sine y. Set this aside because it'll come in later on. Now look at that. Focus on this. We have y is equal to arc tan x over root 1 minus x squared, because each of these individually are functions. This right here is a function, this here is a function. They're independent functions. They just happen to equal to one another, and you have to show why, and that right there is your verification procedure. When you're looking at this, what can you do? The best thing you can do over here is to take the arctan on the other side, and you'll bring in the tangent. Tangent of y is equal to x divided by root 1 minus x squared. Now a good item to do over here is to take this radical onto the other side. You'll have root 1 minus x squared, and you'll cross multiply and attach with tangent y is equal to x. But I know x from right over here was also equal to sine y. You see how from this statement we have x is equal to sine y. We can do this substitution. Now what I can do, you see I have a tan y. If I want, I can clean it out before I do the next step so you can see it better. 1 minus x squared in the root tan y is now equal to sine y, with this x having been removed, because this was equal to that and they're both equal to x, so you might as well remove the x. This is what you're saying. Take the tangent y on the other side. You have 1 minus x squared is equal to sine y over tan y. Sine y divided by tan y is easy. You're looking at a sine over 1 divided by sine over cosine. See, sine y divided by tan y. You can flip things around. You have cosine over sine. You end up seeing just a cosine come out of this. So root 1 minus x squared is now equal to the simplified quotient of this, which is just a cosine y. It wouldn't hurt now for you to get rid of that radical, and you know the best means of getting rid of radical is to square things out, and you square them out. When you square this out, we will come and continue over here. This radical goes where you have a 1 minus x squared is equal to cosine square y. But I also know again x was in all instances always equal to this sine y. If I'm saying that x is equal to sine y, I can substitute that. I'm looking at a 1 minus sine y whole square is equal to cosine square y. When you open this up, you can take this on the other side. You have a 1 is equal to cosine square y plus sine square y. This right here is a trigonometric identity. No matter what you use as a variable, x, theta, t, y, whatever, it's always equal to 1. 1 is equal to 1, and it's done. So this right here was a bit more of a challenging one, but you're done with this. The verification procedure is completed. This indeed is equal to that by the procedure you've seen. The procedure very well involves you or required you to do the substitution twice. You did the substitution once right over here where x was equal to that, and you're seeing it come into play right over here. And the second time the substitution was done was right over here when you brought it in and you utilize this Pythagorean trigonometric identity to do the final completing verification over there. And that right there is the essence of this video. Thank you for watching. Have a nice day.